Hello. I'm going to do a very brief introduction to the idea of buffers and introduce what's known as the Henderson-Hasselbach equation, although I see it spelled recently as Hasselbach. But anyway, never mind, doesn't matter. But a buffer is a solution that will resist a pH change in either direction, whether you add strong acid or base. It tends to not change its pH very much. Extremely important in biology, in our bodies and in all biological systems and in many other systems. It is, the essence of it is it's a mixture of a weak acid and the conjugate base of that weak acid, or a weak base and its conjugate acid. They all work the same. So anyway, what we start with is our standard old equilibrium expression, first for a weak acid. And this is just our generic weak acid, HA. Generally, a carboxylic acid is the most common by far. And we've seen that before. Now, what we're going to do is take the log of both sides. And so, actually, let's put over here in a little side yard. Remember that the log of A times B is going to be equal to log A plus log B. Just remember those things back from your early days in general chemistry. In any case, so what we're going to do is we're going to say log of Ka is equal to the log of hydrogen ion concentration plus the log of A minus over HA. Let me neaten this up a little bit. Get rid of this now that you've got that in your head. Now, let's swap sides here. Let's move the proton term over to the left. And let's move the Ka term over to the right. Now, what is the negative log of hydrogen ion concentration? That's nothing but the pH. And the negative log of Ka is the pKa. And then we put in the log term of the base form over the undissociated acid form. This here is relatively famous as the Henderson-Hasselbach equation. And it was developed kind of in two stages. 1908, Henderson formulated this idea, and then in few years later, 15 to 18, I don't remember exactly, Hasselbach presented it in the logarithmic form. They apparently weren't partners or anything, but anyway, that's the name it goes by. So, a couple of things about this. Notice that if the base and acid form, that is, let's say acetic acid and sodium acetate, or ammonium ion and ammonia, or any pair of acid and its conjugate base. If those two are equal, then that's the log of 1, which is 0. So when these are equal, the pH equals the pK of this acid here in the denominator. And so that is the greatest, gives you the greatest buffer capacity. As it turns out, the concentrations aren't all that important. It's this ratio that's important in determining the pH. But the amounts, both the absolute amounts, you know, molarity, and their ratio are, well, their amounts determine the buffer capacity. How much will it buffer before it ceases to be a buffer. In any case, you can also formulate this in the opposite way. You can say POH is pKb plus the log of the acid form over the base form. I have seen this done, but I don't like to do it because we have pH meters, we don't have POH meters, and it just confuses the issue. For a base, we can set it up the same way because we're going to measure pH with our meter. We're not going to measure POH. We calculate that pH plus POH is 14. But if I say pH equals pKa plus log of the base form over the acid form, and the pK of this acid is what we want. And so for a base, like I'm saying here, use the pKa of the conjugate acid. And like I say, you can do it this way with this POH, and some of the online homework systems use that, and it's up to you. But the way I think is the best to do it, stick with pH, stick with pKa. A lot of your tables give the Ka and pKa values, even if it's a base. It always gives the pKa of the conjugate acid, even for ammonia and things like that. So usually it's best to stick with that. But in any case, that's a very brief introduction. In some other videos, we'll go through the calculations and how all that stuff works. And that'll be enough for this particular recording. So I will see you in another video.